We'll now look at basic 3-bone IK setups. 3-bone IK generally falls under two categories, and these categories can colloquially be referred to as dog legs and spider legs. Of the two, spider legs are generally easier to deal with and are pretty straightforward in KineFX, so I'll start with rigging those. I'll also set up a basic mechanical version of a dogleg IK. I will now start with the spider leg IK. The skeleton node has been used to create the basic limb. I'll add a reorient joints node, and then I'll get a visualize rig node. This is a node which is used to check the transformations. I'll set the joint access style to gnomon, and then increase the size to make them more visible. This reveals a problem with my joints. The joint transformations are not consistent. The most problematic joint is the effector, but I prefer to have no problems with my transforms, so I'll replace all of them. This will be done with the reorient joints node that I've just made. I'll set this to have a Z value of -1, and this gives me much more consistent transforms throughout my joints. Next, I'll get a rig attribute VOP. This is where I'll place my solver. I will also get a rig pose node. This will allow me to manipulate the rig, and I'll get a delete joints node. There are currently 4 joints. I can delete either the second or the third joint. It doesn't matter which, as long as I have 3 joints. In this case, I'll delete the second joint. I want these controls to move independently of each other, so I'll get a reparent joints node. This will be connected to the reparent joints node. I'll add one field to this, and I'll use an asterisk to select all joints. By leaving the parent field empty, it will reparent all of these joints. The rig pose node will be connected to the reparent joints node. This will then be connected to the second input of the VOPs node. The first input of the VOPs node will be connected to my main skeleton. I'll now move my controls. This will allow me to see how the solver affects the limb. I can then enter the VOPs node to add my solver. In this case, the solver will be the standard IK solver. By default, this will take in all the points from input 1. By default, this will be calculating transforms on all the joints from input 1. These joints will be controlled by 3 controls: the root, the goal, and the twist. And the default for these is that the first joint from the second input will be the root, the second joint from the second input will be the goal, and the third joint from this input will be the twist. To set the points, I'll use a set point transforms node. I can then connect this to the solver. I'll need to connect the points port and the transforms port. The leg now snaps into position, but it is not an appropriate position. The reason it is not working properly is that the point numbers for the target controls are not correct. In this setup, the goal is the third point in input 2, and the twist is the second point. When swapped, these values give the correct behavior. This is all I need for basic control of the spider leg. These values, however, can be set manually. For the controls, I can use a getPointTransform node. For this example, I'll set the goal. I'll set the file to second input. The signature that I use will be the name. In this case, I'm using the automatic naming, so the name will be point3. The target objects are set by an array of transforms. To get an array of transforms, we'll use the getPointTransforms node. I will be setting these using the first input. For these, the signature is group, and I'll get these groups by specifying the name attribute. Attribute name is equal to point 0. I'll also need to individually reference the name attribute for point 1, point 2, and point 3. So this gives me a basic spider leg. Unfortunately, this approach will not work for the dogleg rig. We'll now take a look at the dogleg rig. I can enter the geometry node. I've used the skeleton node to create my bones. Once again, I'll use the reorient joints node to correct the transformations. I will set these to use a -1 and Z, and I'll check the consistency of the transformations using the visualize rig node. I will not be deleting any of the points from this rig, but I will need a reparent joints node, not because these points need to be independent of each other, but because they need a hierarchy. I'll then get a rig pose node to manipulate my joints, and I'll get a rig attribute VOP to use for my solver. As stated earlier, I'll be using a mechanical solution for the dogleg rig. The reason for this is the dogleg will currently need a custom solver. While I may make a solver in the future, this solution is more than sufficient at the moment. Before we build the dogleg rig, we'll need to understand the problem we have with the current solver. I'll set the point positions, and I'll set the goal to be my final point. The twist will be the second last point. And as you can see, the solver automatically gets rid of our dogleg. The difficulty with IK with more than 2 bones is there are multiple solutions for the IK. Because of this, most of the solvers will iterate over an algorithm multiple times. This iteration makes complex solvers far slower. The current solver tends to have a more smooth interpolation and does not come with controls to limit internal rotations or to specify alternate rotations. There is nothing wrong with this, as it does give us a faster solver, but it does mean that in cases like the dogleg, we'll have to work around its limitations. We will still be using this solver, however. Get a set point transforms node. In this case, however, we'll only use the first 3 joints from the first input. Those would be point 0, point 1, and point 2. I'll also specify the controls manually. In this case, point 0 will be the root, point 2 will be the goal, and point 1 will be the twist control. This will create a standard IK for the first 2 bones of the leg. I'll add a visibility node as I do not need to see how my controls are parented. This will allow me to more clearly see how my bones are reacting. I will now reparent these controls. I will be using a reverse control setup. First, I'll unparent all my joints. My joints will now move independently of each other, and I'll now start reparenting these joints. This will reverse how they were originally parented. Point 3 will be the parent of point 2, and point 2 will be the parent of point 1. This will allow the effector to control both the position and the rotation for the leg, and it will maintain a level of independence for the twist controls. I'll then get a second rig attribute VOP. Using a second node prevents any ambiguity from reuse of points. The output of the first rig attribute VOP will go into the first input port, and the output of the pose node will go into the second input port. This is where the reorient joints node will come into play, as you can often get unexpected results if the transforms have not been set correctly. I will get a lookat node. This will be the KineFX version of the lookat node. I'll make the final joint look at the effector control. First I'll need to get the joint. and I'll use the get point transform. This will be from the first input, and it will be 0.2. I can then set the point transform. I'll get the point information from the get point transform node, and I'll get the transform from the lookat node. To set the 2 value on the lookat node, I'll use another get point transform node. This will get the point from the second input. This point is my effector, and it will be 0.3. And now my solver should be working. I've set up my coordinate space to work with the lookat control. If you are working with a different coordinate space, you may have to adjust these parameters. This is also where you'll get errors if the transforms are not consistent. And this will complete the basic dogleg rig. And we should now be able to build basic 3-bone IK systems.